June 21, 2001, deep in Western Australia. A single freight train stretches 7.3 kilometers across the Pilbara Desert, 682 iron ore wagons, 8 diesel locomotives, one driver controlling nearly 100,000 tons from a single cab. The United States runs the largest freight rail network on Earth and cannot reliably operate a train half this length without blocking intersections, strangling passenger services, or folding rail cars off the tracks. The difference isn't horsepower or better technology, it's what the Pilbara doesn't have. The Pilbara is a stretch of red desert in northwest Western Australia, roughly the size of California. Almost nobody lives there. What it does have, buried under that ancient soil, is one of the largest iron ore deposits on the planet. Western Australia holds 98% of the country's reserves, and nearly all of it sits here. Every year, hundreds of millions of tons leave the desert for coastal ports, most of it feeding Chinese steel mills that consume raw material on a continental scale. Moving that volume demanded a rail network without parallel. 5 private railways crisscross the region, each owned by a different mining company. BHP runs 2 lines. Rio Tinto operates over 1,700 kilometers of track serving 15 mines. Fortescue built its own railway from scratch in 2008, not by choice, but after Australian courts rejected its bid to share BHP's tracks. When a competitor would rather lay hundreds of kilometers of new rail through empty desert than accept a legal defeat, you start to understand what the ore underneath is worth. Roy Hill completed its own 395-kilometer line in 2015. Combined, more than 3,800 kilometers of heavy-haul track, all privately built, all privately maintained. Every one of these railways does exactly one thing: haul iron ore to Port Hedland, the world's largest bulk export port, which handled over 500 million metric tons in 2018 alone. No passenger services, no mixed freight, no grade crossings every few hundred meters, just ore, locomotives, and empty desert. That emptiness is not scenery. It's the most critical piece of infrastructure on the entire network, because it isn't the locomotives or the wagons that make 4-mile trains possible. It's everything the builders never had to work around. The rail itself is heavier than anything on a conventional network, 68 kilograms per meter, laid on concrete sleepers engineered to absorb the highest axle loads in the world. Curves are gentle because surveyors drew these lines through open terrain with no cities forcing detours. Signaling systems handle one type of traffic moving in predictable patterns. Even the passing loops where opposing trains wait for each other stretch long enough to hold consists measured in kilometers. Every component answers to a single question: can it carry ore? A standard BHP train runs 3 locomotives hauling 224 wagons, roughly 26,000 tons per trip. Up to 9 of those trains roll through the Mount Newman line every day. But the detail that quietly makes all of it work is uniformity. Every wagon carries the same commodity loaded to the same weight. Identical mass, identical handling, car after car for miles. On a mixed American freight train, a light, empty hopper sitting 3 cars behind a loaded liquid tanker creates slack action, a violent accordion of forces that can snap a coupler or jackknife a consist on a curve. Mismatched weight punishes length. In the Pilbara, that punishment doesn't exist. Every car pulls the same, brakes the same, and responds to momentum the same way. Engineers can safely stretch a consist to 4 miles because the forces inside that train behave like a single object, not a chain of competing ones. That uniformity made extreme length survivable. The economics of the desert made it mandatory. The 2001 record run covered 275 kilometers of its 426-kilometer route from Yandi to Port Hedland before BHP ended it, not because something failed, but because they had the data they needed. BHP's Vice President of Rail, Mike Darby, put it plainly: if you don't keep trying different things, you'll never know what you can do. That train wasn't a spectacle. It was a stress test, for a system designed from the ground up to answer one question: how much ore can a single departure carry before the physics breaks? The math drives everything. Every extra wagon per train kills a trip somewhere else in the schedule. Fewer trips means fewer locomotive hours, fewer crew rotations, a lower cost per ton arriving at port. When the entire business model depends on hauling hundreds of millions of tons at the thinnest possible unit cost, the pressure to stretch every consist doesn't relax. It compounds. Rio Tinto took that same logic and removed the most expensive variable left: the driver. In 2018, Rio Tinto completed the world's first fully autonomous heavy-haul train journey on its Pilbara network. By 2020, the entire auto-haul system was running. Today, 220 iron ore trains cross the desert without a human hand on the throttle, monitored from an operations center in Perth, 1,500 kilometers from the nearest locomotive. The company calls it the world's largest robot. Think about that. 220 trains, millions of tons of cargo, no crew on board. Autonomous operations work in the Pilbara for the same reason 4-mile trains work. No school buses at crossings, no passenger trains needing to pass, no switching yards sorting mixed freight. Closed system. One commodity, one direction, one destination. But a system that eliminates human error still has to reckon with human-sized mistakes. November 2018. A BHP driver steps off a loaded train, 4 locomotives, 268 wagons, to inspect a problem car. While he's outside the cab, the train rolls away. It traveled 92 kilometers unmanned, averaging 110 kilometers per hour through open desert. BHP's remote operations center in Perth tracked every meter from 1,500 kilometers away. The solution was deliberate destruction. Operators switched a set of track points and forced the train off the rails. The wreckage shredded 1.5 kilometers of track and hundreds of ore wagons. Nobody was hurt. Nobody could have been hurt. The train was rolling through unpopulated desert on a private line with no grade crossings in its path. A runaway on any other railroad network on Earth is a disaster measured in casualties. In the Pilbara, it was a repair bill. Expensive, embarrassing, but absorbed by a landscape that offers the one thing no engineer can manufacture: distance from people. The American freight network operates without that margin. 140,000 miles of track threaded through 212,000 places where a train and a vehicle can meet at the same level. Texas alone has over 15,000 grade crossings. Illinois has more than 12,000. In the Midwest and West, where towns were built on grid patterns, some stretches stack a crossing every few hundred feet. A Pilbara ore train can travel 400 kilometers without meeting a single public road. An American freight train can barely cross a county. Sharing that same infrastructure is Amtrak, which runs passenger services on tracks owned by freight companies. Federal law requires freight railroads to give Amtrak dispatching preference. In practice, the freight carriers routinely ignore that requirement because enforcement has no teeth. In 2023, freight interference caused over 900,000 minutes of delay to Amtrak passengers, more than a year and a half of cumulative waiting time in a single calendar year. The regulation exists on paper. The railroad exists on steel. Steel wins. Longer trains tighten every one of these choke points. A 2-mile consist blocks a grade crossing for minutes at a time. It can't fit into sidings that were built decades ago for shorter trains, so it stalls every other movement on that stretch of track, freight and passenger alike. And the physics of controlling a mixed cargo train at that length, different commodities, different weights, different handling characteristics fighting each other through every curve, is a fundamentally harder problem than managing a uniform ore consist on flat desert rail. Mismatched weight breeds unpredictable forces. Unpredictable forces punish length. Length is exactly what the industry kept adding. If you're finding this comparison useful, subscribe. We break down infrastructure engineering and heavy freight logistics every week. But the reason the trains kept getting longer isn't an engineering story. It's a Wall Street story. Hunter Harrison built the model at Illinois Central in the late 1990s and gave it a name that sounded like engineering: precision scheduled railroading. The principle was simple: run fewer trains, make them longer, hold them to strict schedules, and cut every cost that doesn't directly move freight. When Harrison brought PSR to Canadian National and later to CSX, the other Class 1 railroads watched the stock price and followed. By 2022, 6 of the 7 largest freight railroads had adopted some version. The financial results were staggering. Between 2011 and 2021, the 7 largest carriers cut their combined workforce by roughly 28%. Some subdivisions lost half their employees. Union Pacific alone shed over 10,000 jobs in under a decade. Operating ratios shrank, dividends climbed, and Wall Street applauded every quarter that moved more tonnage with fewer hands and less equipment. The median American freight train now stretches about 5,400 feet, roughly a mile. But that median hides the extremes. A 2025 review of Union Pacific's Southwest Corridor found that 10% of trains exceeded 2.5 miles, running routinely on corridors where the sidings, the signals, and the remaining workforce were all sized for shorter consists. In the Pilbara, longer trains followed infrastructure: heavier rail, longer loops, autonomous signaling, all built before the trains grew. In America, the trains outgrew the track first. The infrastructure is still catching up. Railroad workers had been warning for years that the gap would produce a failure. On the evening of February 3, 2023, it did. Norfolk Southern Train 32N was rolling east through Ohio. 149 cars, 9,000 feet of train, 1.7 miles. 20 of those cars carried hazardous materials, including vinyl chloride. The 23rd car had a wheel bearing that had been running hot for miles. A trackside sensor in Salem, Ohio, 17 miles from East Palestine, caught the elevated temperature and flagged an alert. The analyst who reviewed the reading classified it as non-critical. Minutes later, the bearing collapsed. 38 cars derailed in the middle of a small town. 3 tank cars split open on impact. Fires climbed out of the wreckage, and more than 2,000 residents evacuated from a 1-mile radius. Then the response made everything worse. Norfolk Southern recommended a controlled burn of the vinyl chloride cars, which sent a massive column of toxic smoke drifting over the town. The National Transportation Safety Board later determined the burn had not been necessary. Norfolk Southern had fed incomplete and misleading information to the local incident commander who authorized it. The company settled with the EPA for $310 million. At one point, 7 miles, Train 32N was actually shorter than many modern freight consists. The disaster didn't need an unusually long train. It needed the conditions that longer, leaner operations had quietly normalized. Overheating bearings traveling miles between widely spaced sensors, hazardous materials mixed into ordinary freight through residential neighborhoods, and a shrinking workforce with fewer inspectors to catch failing equipment before it fails catastrophically. Australia runs trains more than twice that length through open desert with no crew on board, and the safety record holds. But those trains don't roll through anyone's hometown. Could America build a Pilbara-style railroad? The physics would cooperate. Distributed power, autonomous operation, advanced train control. Every technology exists and works today. The Powder River Basin coal railroads in Wyoming already run something close, but even those trains share track with other freight and pass through communities with grade crossings. A true dedicated corridor would mean buying right-of-way through populated land, eliminating hundreds of crossings, separating freight from passenger traffic, and negotiating with every city council along the path. No Class 1 railroad will take that on, because shareholders measure success in quarterly operating ratios, and infrastructure that pays off over 30 years looks like dead money on a balance sheet that reports every 90 days. The Pilbara railroads never solved those problems. They never encountered them. Empty desert, ore in the ground, port on the coast, and nothing in between. The only question was how much steel and diesel it would take to connect mine to ship. For American railroads, The question has never been that clean. The network carries everything for everyone through everywhere, and the trains keep stretching on corridors that were never built to hold them. That single driver crossing the Pilbara in 2001 with 682 wagons behind him wasn't commanding an extraordinary machine on an ordinary railroad. He was commanding an ordinary machine on an extraordinary landscape, one where the only engineering problem was tonnage, because every other problem had been solved by geology and absence. The next video goes inside the consist itself, how Rio Tinto's autonomous system sequences 226 wagons so that a train flexing across 7 kilometers of desert track doesn't tear itself apart on a curve that looks perfectly straight.